Okay, as just announced, I'll be talking about antimatter, and I'm going to give you sort of an overview of what we know about antimatter and why we're studying it, but also a little bit about what it's useful for. But you've been listening to lectures for an hour now, and so actually it's probably a moment for a short break, and I'm going to show you a movie which you may already have seen or not, which deals with antimatter. It deals with, sorry, there we go. That's why it's not moving. It deals with antimatter the way Hollywood sees antimatter. And this is a movie that you may have heard of, Angels and Demons. And I'm just going to let the movie run while you're watching it. Comment a little bit on what you're seeing. In fact, you'll recognize some of the images because you've already seen them before in the first two speakers' presentations, or actually in the first speaker's presentation. It's the Large Hadron Collider. It's CERN's Large Hadron Collider. And the experiment you see here is not the compact muon spectrometer that you just saw before. This is the ATLAS experiment, which is twice as big in every dimension. It's a 6-story building, 45 meters long, 40 meters high, and 40 meters wide. And just like the compact muon spectrometer, it's there to see collisions of particles at very high energies, which happen at its heart, and occasionally produce antimatter. And this antimatter in the movie is led down the LHC, only they've added a small detour onto it, and so it's actually channeled off to the side and stored in these little traps where it's accumulated, and then, once it's been accumulated, it's taken away. And the story of this movie basically gyrates around the fact that it's stolen from CERN and hidden in the Vatican. And the idea is, of course, to blow up the Vatican. So the whole thing is a race against time to try to save the Vatican and lives, to avoid the annihilation of the Vatican. Now, there's a tiny fraction of truth in that movie. It's not really reality. Antimatter exists, definitely, and it is produced at CERN. And a few grams of it would be enough to destroy Rome. Actually, not just the Vatican, but the whole city of Rome. And so the question is, what is antimatter? And how do you deal with it? And how do you trap it? In the picture, you can see trapped antimatter. And I'll show you another trap of antimatter in a little while. Antimatter is something that comes from a very simple equation. E is equal to mc squared. When you transform energy into stuff, you're going to get mass, matter. So you can transform kinetic energy, for example, from colliding particles into new particles. Except that when you have that equation up there, you can't just produce a particle out of energy. Think of a particle like a proton. It has a positive charge. Energy doesn't have charge. So you can't just produce one proton. You have to balance the charge by producing a second particle, which has exactly the opposite charge of the proton. An electron, an anti-electron, proton, antiproton, a neutron, a neutral particle, also needs to be balanced. Because the neutron itself consists of quarks. So the anti-neutron consists of antiquarks. Every particle has its opposite antiparticle. And they're always produced in pairs. This is what it looks like when you produce a particle pair, an electron and anti-electron, from light hitting a nucleus. You can see the anti-electron and the electron with two photons interacting with each other. Except you see a third line there, and that's sort of destroying my story, except that's the nucleus that's recoiling against, that's been hit by the photon. So it's actually okay. You always get pair production. Matter and antimatter, however, once they're produced, can go back together again and can transform back into energy. They can annihilate. And they can disappear. This energy can then retransform into new particles and antiparticles. You can get this chain of particle-antiparticle creation and destruction processes going on one after the other. If you go back to the Big Bang, when there was a lot of energy in the universe, E is equal to mc squared, all this energy transformed into stuff, but right after what I told you, it had to have produced as much stuff, as much matter, as anti-stuff, antimatter. So what you expect is that at the moment of the Big Bang, or right after the Big Bang, you get a 50-50 universe. 50% matter, 50% antimatter. And this is what the universe should still contain right now. Now, if you want to measure the composition of the universe, you have to detect the fact that a particle is a particle, and antiparticle is an antiparticle. And they have identical properties, except for the opposite sign. And this is something that comes from our description of how these particles are formed and how they interact with each other. Now, all the atoms that surround us are made of particles. And so the atoms' properties are defined by the properties of the particles. And if I form anti-atoms, which are made up of antiparticles, their properties are going to be defined by the properties of the antiparticles, which are the same as those of the particles. And so anti-atoms and atoms are actually indistinguishable. They look exactly the same. And so in particular, what's going to happen is if I try to look at the light emitted by an atom and by an anti-atom, I will see no difference. Stars and antistars look exactly the same. The only way I can detect antimatter is actually by annihilating with matter. And so I have to live off the fact that anti-atoms and atoms come together somewhere. In some parts of the universe, galaxies and anti-galaxies could collide. And if they collide, then at that point, I can see the annihilation that produces light. This annihilation is basically the annihilation between an electron and an anti-electron. And this produces two photons that are blue, very, very blue. They have an energy of 511 keV, which corresponds exactly to the mass of an electron. And so it should show up, this light. If I look at the normal sky, here you can see a picture of the sky at night where you see the Milky Way. And this is all the colors that you can possibly see, from blue to red. And I can expand this with better telescopes to go all the way to the infrared, all the way to X-rays. But it always looks more or less the same. But if I put a narrow window, a filter on this telescope to look at exactly the color that annihilation of electrons with anti-electrons produces, then this is what the universe looks like. You only see a blob at the center of our own galaxy. There's a huge amount of antimatter at the center of our own galaxy. In fact, since our own galaxy has come into existence, about 5 billion years ago, this corresponds to the annihilation of 3 suns worth of antimatter with matter. That's enormous. But that's not what we're looking for. We're looking for 50%, and our galaxy contains hundreds of billions of stars. So if our galaxy contained any antimatter, you should be seeing hundreds of billions of times that signal there. And any anti-galaxies out in the universe would also glow when they collide with galaxies. And so what this actually shows is there is no antimatter in the universe. We don't see any. Not through light, nor through detectors that are floating above the atmosphere. You can build a detector. This is the alpha magnetic spectrometer that is sitting on the International Space Station that measures all particles coming from the galaxy and from outside the galaxy and that fly through it. And for each particle that flies through it, it asks the question, is this a particle or is it an antiparticle? Neither of these two methods have seen any antimatter in the universe. And so we've got a problem. This is what the universe looks like in matter. And on the antimatter side, it's completely empty. And this is in total contradiction with what I just told you, that the properties of matter and antimatter are the same, and that we should have a completely symmetric universe. Equal amounts of matter and antimatter. So what I've been telling you is wrong. It's completely wrong. You can't get worse than that. In fact, what we have is something that has killed off all the antimatter, but has left a little bit of matter over. And this little bit of matter is everything that we see. The whole universe that we see is just a leftover of a huge fight at the beginning between Dr. Jekyll, on the bottom right, and Mr. Hyde. And Mr. Hyde, unfortunately, has won the battle. He's the one who's left over because all the Dr. Jekylls are dead. They have disappeared. The universe is unbalanced. We don't know why. We don't have a clue yet. And the idea is to try and figure out what's gone wrong with our models of physics, to try and understand how we could end up in a situation where we don't even understand the composition of the universe. And the way to do that is to try to put together everything we know about the universe and look at it. This is a picture of the evolution of the universe since the Big Bang. On one slide, 14 billion years ago is the dot on the left-hand side, and we're here on the right-hand side, and it shows in different time windows how the universe looked like. So if you want to look at the universe right now, we're sitting up there somewhere and looking outwards, looking backwards in time, and looking at what we can see. And with telescopes, we can sort of look at the crime scene. We can look at what we can see of the universal formation, the evolution of the universe since the moment of the Big Bang. And it's sort of a crime scene investigation which turned up the problem that we have a disappearance of antimatter. Now, in order to figure out what happened, how the antimatter could have disappeared, we have to actually do more than just look outwards. We have to reconstruct the crime scene. We have to go back to what happened at the moment of the Big Bang and look at antimatter as precisely as we can and try and figure out what's going on. And this is happening at CERN, at the European Center for Nuclear Research in Geneva. It's just another picture of what you saw before. There's a tiny little area inside CERN, and in fact it's the only place in the world, where antimatter is produced in order to be studied and compared with matter. This is the accelerator, view of the accelerator with 6 experiments. This is the whole world's community of experiments looking at antimatter and trying to figure out whether there's a difference between matter and antimatter. And what they're looking for is to try to see where this asymmetry is coming from. You can look for the properties of antimatter, of individual antiparticles or atoms made of antimatter, and then you're testing fundamental symmetries, like charge symmetries. Physics is the same, whether you have an electron or an anti-electron. It's the same whether you have a proton or an antiproton. That's the charge symmetry. It's the same whether you're looking in a mirror or looking at reality. If I look in a mirror and I drop a ball, I will describe it exactly the same way. And this is the mirror symmetry. And in fact, this ball, I can also film it, run the movie backwards, and even then, the physics, the description is the same. So this is the time symmetry. Physics should not depend on any of these being different. And what you can look at is the color of light emitted by antihydrogen atoms, atoms made of an antiproton and anti-electron, or of hydrogen atoms, a proton and electron, and see if you can see a difference. And the reason why you choose light is that's something you can measure extremely precisely. You can measure a color incredibly precisely. In the case of hydrogen, you can measure it to 1 part in 10 to the 15. That's a millionth of a billionth precision. You can also try to ask yourself whether antimatter and matter interact differently somehow. And so you're looking at coupling of antimatter to forces, to the gravitational interaction, to the strong interaction, the weak interaction, the electromagnetic interaction. And one of these has not been studied yet, and that's the one we're focusing on. Now, the difficulty with all this is in order to study these antimatter systems, you have to make them. You have to put them together. You have to make an atom of antimatter, and then you have to hang on to it. So making the first antihydrogen atoms took about 10 years, and it was successful in 2002. Trapping, hanging on to the first antihydrogen atoms, was successful in 2010. And since then, it's taken 8 years to be able to measure the color of antihydrogen. Just last year, the color of antihydrogen was measured for the first time and compared with hydrogen to a precision of a millionth of a millionth. And up to now, no difference has been seen between the two. So maybe one has to be more precise, and that's what the experiments are doing. Or they have to come up with completely different ways of looking at antimatter. And this is the next big question. It's testing gravity with antiatoms. There are 2 ways to do that, to drop something. You can drop it while you're holding it in a trap. You open up the trap, out it will fall. But in order to hold it, it has to be extremely cold, a millionth of a degree above absolute zero, in order for it not to move too fast so that you have time to see it drop. The other possibility is to shoot it out of a cannon. Shoot the cannonball, it'll fly on a parabolic trajectory, and you measure the parabolic trajectory. And so I'd like to show you a picture of what some of these experiments looks like, or actually one of these experiments looks like. And this is the cannon. You've got the cannon here on the left-hand side. The whole thing is about this big, inside an apparatus that's about 3 meters in diameter. And out of this cannon should come antihydrogen atoms. And if they're moving really fast, they're almost not going to fall. They have no time to fall, so they fly on a straight line. You turn on gravity, or you get them to move slowly, they'll actually move slow enough that they can fall downwards on a parabolic trajectory. And with numbers that you can think of, reasonable numbers, they're going to fall by 100th of a millimeter, the thickness of a third of my hair, over a distance of 1 meter. And if they then hit matter, they will, as they touch matter, annihilate. And as they annihilate, they will disappear. So you can see where they disappear, and as they disappear, they produce other particles which you can then try to track. You do this for many, many different particles, and many different antihydrogen atoms, and you accumulate these many different lines, and you compare the average by how much they have fallen with respect to a straight line, and you've measured gravity. But you need a detector that is able to see something at the level of a 100th of a millimeter. And there is only one type of detector in existence right now that has that kind of resolution, and it's a detector that was invented over 150 years ago. We need new detectors like this. We're not anywhere near this kind of detector. This is a photographic plate. Photographic plates are incredibly sensitive, they're incredibly precise, and they can measure the point where the antihydrogen atom hits the plate to 1 micron, a thousandth of a millimeter. You see here several points where antihydrogen, or actually antiprotons have hit the emulsion, and every time they hit this emulsion, this photographic plate, they fragment a nucleus of silver or of bromine and break it into fragments. These fragments explode all over the place, and you can track them in the emulsion and find out where they come from. In fact, one of the things we have to worry about is this is just a two-dimensional photo. Actually, it's a three-dimensional image because this is a thick emulsion. You can scan through it. It's about 50 micron thick. And as you scan through it, you can see that you get these lines going through it that you can reconstruct and find out where the antihydrogen atom has annihilated, whether on the surface or somewhere further away. So this is all fine and dandy. We're really looking into the fundamentals, trying to figure out why the universe is not empty or why it contains no antimatter. But there are also other possibilities that you can have with antimatter. You can use the antimatter for some useful stuff, and I'd like to spend the next few minutes talking about what you can use antimatter for. One of them is to look inside the body. One of them is to treat tumors, just like the previous speaker has talked about. You can also think of using antimatter as fuel for spaceships, and then there are some other ideas that I'll briefly present. So the first one is using antimatter to look inside the body. You saw something like that before. It was a MRI, a magnetic resonant imaging device. This is not an MRI. This is a PET scanner, a positron emission tomography detector. And the way it works is that you put the antimatter inside the body by inserting inside molecules that are relevant for physiological processes a isotope that emits anti-electrons when it decays. So this can be carbon-11, it can be nitrogen-13, it can be oxygen-15. Mostly it's fluorine. And these molecules are then injected in the bloodstream, are spread out through the body, and are taken up inside those cells that have a receptor or a need for those molecules. So it can be, for example, if you inject a sugar, which has been radioactively labeled, this sugar, this glucose, will be absorbed by cells that need lots of energy and that are going to absorb that. But it can also be signal transmitters, and I'll talk about that in a minute. Once you injected this in the body and the cell that has used the molecule, then the radioisotope is going to sit there inside that cell until it decays, emits an anti-electron, and the moment the anti-electron is emitted, it'll annihilate with an electron, produce 2 photons. These photons come out back to back. So here, for example, you can see 2 photons coming out and being detected by crystals, big heavy crystals that come from experiments in particle physics. You create a coincidence between these 2 signals. You know that somewhere along that line there's been an emitter, and then you run this for many, many times. You watch the patient for minutes while many different radioisotopes decay, and you get many different lines that intersect in space, and they tell you exactly where the source of these photons is. And that allows you to pinpoint with millimeter accuracy the source of these emitters, which can, for example, be cancer cells. Cancer cells have a high metabolic rate, and so they will need a lot of glucose, also radioactively labeled glucose, and so you can pinpoint cancer tumors at a very early stage. 100 cells is enough to see this. And with that, you can create a 3-dimensional image of the body and see where these emitters are sited inside the body. So what you see here is a patient where you see several structures inside the body which produce a lot of photons, which have used up a lot of radioactive sugar. First of all, at the top, you see the brain. The brain is one of the biggest users of glucose in the body, so no matter what you look at inside the rest of the body, the brain is going to light up. You also see the heart and the kidney, and you see the bladder. The bladder is where most of this radioactively labeled glucose ends up. But you also see in the middle of the body here the liver and metastasis. And so this patient, unfortunately, has tumors that you can detect this way and then think about treating. But of course, you can do other things. You don't just label glucose with radioisotopes. You can also label other molecules, serotonin, dopamine, amyloid-binding molecules. You can put it into opioids, and you can put it into a number of medication that you're trying out to see where they're being absorbed. So you can follow where the brain absorbs certain molecules, and you can look at if you can see a difference between men and women in terms of, for example, their serotonin uptake. And as you can see, you'll have a hard time distinguishing the male on the left-hand side from the woman on the right-hand side. But that's not the case for all molecules. It's not the case for all medically relevant molecules. And so this actually allows you to see what's happening, how the body deals with different pharmacologically relevant molecules. It also allows you to try to study the function of the brain, because you can look at where the brain is active, where it's using up the most part of its energy, and you can distinguish areas inside the brain, for example, that are active when you're hearing words, or when you're seeing words, or when you're thinking words, or when you're speaking words. And this allows you to create a functional map of the brain as well, with positron emission tomography. Now, I'll come back to the tumors, because once you've found a tumor, you want to treat it, and as the previous speaker has just explained, radiotherapy is one way of treating tumors. And this is just another picture like those that he's already shown, where on the left-hand side, you see the dosage deposited by X-rays on the left part, and on the right part, you see the damage deposited by protons. And you see immediately that protons leave more damage at the end of their trajectory, X-rays more damage in the beginning part of their trajectory. Now, like every good thing, you can do better. And so a few years ago, we started wondering about whether, if you replace protons with antiprotons, you might actually be getting something more powerful than protons. Because if you remember back to the photographic plate that I showed you, when the antiproton annihilates, it produces these nuclear fragments, which behave like the carbon ions that the previous speaker talked about. Only this time, the carbon ions are inside the tumor. And so they should do much more damage inside the tumor, but the entering beam is just a proton, or an antiproton in this case. So the expectation is that antiprotons should be more effective than protons. And so in order to do this, to measure this, to perform a test of this idea, we built a detector. We built an apparatus that looks like what a physicist thinks a human being looks like, which is basically just an aquarium. An aquarium with a test tube in the center, and in this test tube, suspended in gelatin, we had a bunch of living hamster cells that were irradiated with X-rays, with protons, with antiprotons, and with carbon ions. And we then compared, for each of these different radiation types, what kind of effect they had, how effective they were at killing cells, how lethal they were. And since you've already seen this graph for protons and X-rays, I can now show you what it means in the case of antiprotons and carbon ions. So the photons, again, do their damage all over the place. That's not really good if you want to target something at 15 centimeters depth. The protons are really good because you can target them to stop at 15 centimeters depth. In green, I've compared what we get for protons to antiprotons. And what you see immediately is that for the same amount of damage where the antiprotons stop, they do a lot less damage as they come in. Now, this isn't necessarily relevant if you have such a narrow stopping point in the case of protons or antiprotons. But just as it was explained to you before, that you try to draw the tumor with protons by changing their energy, all these red lines accumulate. They add up. Every time you reduce the energy, you're going to add up another of those in the entrance channel. So in the end, you're going to have only a tiny bit more damage done to the tumor with protons than you're doing to the entrance region. With antiprotons, you can go down pretty much a factor of 4 with respect to the protons. Now, before you get too excited, there's a small drawback. This is premature. We've only treated living hamster cells in test tubes with this, and they were actually healthy. So we need to show that this works for tumor cells, for human tumor cells, and ideally, of course, in patients. So this is where the physicist comes in. For me, the job is done, but actually, it's only a tiny bit that's happened up to now. And then there's another problem, which is that it is far too expensive. To make antiprotons, we need the full infrastructure of CERN. We don't just need a small proton accelerator. So we need development. We need new ways of making a beam of antiprotons, which means we need new technologies for accelerators. that can bring the cost down. Of course, if we can make antiprotons more cheaply, we can also think about using them for something else, which is fuel. Because this is really the maximally efficient way of bringing fuel into a rocket. Normally, when you bring a chemical fuel into your rocket, you're throwing away almost all of it. If you bring nuclear fuel into your rocket, you're throwing away 99% of it. With antiprotons, you would use all the fuel completely. So it's the most efficient fuel that you can think of. Unfortunately, you need to make it. Now, if we don't have an accelerator, we can use you, actually, as producers of antimatter. You're actually producing antimatter right now while you're sitting here. A body of 80 kilograms produces about 180 positrons per hour. And this is simply because you've absorbed a certain amount of radioactive potassium that's been there since the beginning of the universe. And occasionally, it'll decay and produce an anti-electron. A good unit to keep in mind, one banana produces one anti-electron per hour. And, okay, one anti-electron is not a lot. We're going to have to do a little bit better than that. The question is, how much better? We need about a gram of antimatter to have the equivalent of about 10 kilotons of TNT, which is sort of going to get you into the game of rocket fuels. At CERN, we produce somewhere between 10 million and 100 million antiprotons per second, which means somewhere between 10 to the 14, 10 to the 15 antiprotons per year. Now that corresponds to a tenth of a billionth of a gram. In order to get 1 gram of antimatter, you're going to have to run the accelerator at CERN for 10 billion years. That'll just get you the equivalent of 10 kilotons of TNT. Financially, the cost of this is 20 million billion pounds. A lot of money to get 1 gram of antimatter. If you just harvest what CERN is making in terms of antimatter for 1 year, you'd end up with enough power to run a lamp for about an hour. And if you were thinking of collecting bananas to make the antimatter, 10 to the 20 bananas, that's like an Earth-size banana pile, will just about produce 2,000 watts, which isn't really impressive. So we're really talking about not using antimatter as fuel for spaceships, but maybe for something else. And this something else might be to think about selling antimatter. You know, go into fintech with antimatter. And I wanted to compare the cost of antimatter with that of matter. One of the more expensive pieces of matter is gold, which comes in at about 40,000 pounds per kilogram. Antimatter, positrons, are about 40,000 pounds per gigabecquerel. That's 1 billion disintegrations per second. You get 1 billion positrons for the same amount of money. And if you just compare the two, you find out that antimatter is 10 to the 13 times more expensive than gold. It's 10 to the 13 times more valuable. And obviously, if you have something valuable, you want to use it to open up a bank. This is the first bank of antimatter, which has deposits guaranteed in antimatter. And you can buy shares of this bank by depositing a few, micrograms of antimatter. And in fact, the problem is that if you have some money in this bank, you shouldn't carry it around with you, because it will just annihilate in your pocket and leave you as poor as you are right now. Thank you for your attention.